Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. Imagine a world without sunlight, devoid of free oxygen, crushed by immense hydrostatic pressure. This isn't the landscape of an alien planet, but the Earth's deep subsurface and ocean sediments. In these extreme environments, where conventional life struggles, a genus of microbes performs an act of true alchemy. They breathe metal and, in doing so, invent entirely new minerals. Meet Geobacter. These microorganisms are masters of the anaerobic domain. Like us, they need to shed electrons generated during metabolism to produce energy. If oxygen is scarce, they must find an alternative electron acceptor. For Geobacter, that acceptor often comes in the form of metal oxides, specifically, ferric iron, or rust. They are, quite literally, metal breathers. But how does a single-celled bacterium transfer electrons to a solid metal surface that might be several cell lengths away? The answer lies in one of the most astonishing biological discoveries of the last few decades: microbial nanowires. Geobacter and its relatives produce long, conductive protein filaments that extend out from the cell wall like microscopic cables. These nanowires act as biological conductors, establishing a direct, electrical connection between the bacterial metabolism and the solid metal target, facilitating a process known as extracellular electron transfer, or EET. The act of EET is the key to their mineral-making prowess. When Geobacter transfers electrons to the metallic compound, it changes the metal's oxidation state. For instance, reducing highly soluble uranium, V, to the insoluble uranium, IV. This instantaneous chemical transformation causes the metal compound to precipitate out of the liquid solution and solidify. Crucially, this precipitation isn't random. Because the electron transfer happens precisely where the nanowires interface with the environment, often directly on the cell membrane or along the wire itself, the resulting mineral deposit is highly ordered. This focused biomineralization can create nanoscale crystals and compounds that possess unique electrical, magnetic, and structural properties, sometimes forming entirely novel mineral phases that would not appear in purely chemical reactions under those same conditions. The pressure inherent to their habitat adds another layer of complexity, often favoring tighter, denser packing of the emerging crystalline structures. The microbes are essentially functioning as tiny, high-pressure bioreactors, directing geology at a nanoscale. This process is far more efficient and specific than conventional chemical weathering or sedimentation. Consider the implications. In nature, Geobacter plays a massive, often unseen, role in the biogeochemical cycles of iron, sulfur, and carbon, fundamentally shaping the composition of the deep crust. Scientists have observed similar processes involving other heavy metals. For example, some microbes can reduce soluble gold ions into tiny, pure gold nanoparticles, suggesting a biogenic route to mineral wealth, albeit on a very small scale. In the realm of applied science, this microbial alchemy is a game-changer for environmental cleanup. If we can harness Geobacter's ability to reduce toxic, mobile forms of contaminants like radionuclides, such as uranium, into stable, insoluble solids, we can effectively immobilize and neutralize polluted groundwater. They become nature's self-assembling bioremediation system, isolating heavy metals and transforming polluted sites into geologically stable areas. Furthermore, the study of Geobacter's conductive nanowires has inspired bioelectronics. Researchers are exploring how to use these naturally occurring, electrically active filaments to develop living batteries or microbial fuel cells, generating clean energy from waste products. This little deep-sea microbe, thriving under pressure, offers a blueprint for sustainable technology. The presence of Geobacter challenges the classic definition of geological processes. It proves that the formation of complex, highly structured minerals isn't solely the domain of heat and pressure deep within the mantle, but is actively driven by life itself, even in the most inhospitable corners of our planet. They remind us that the interface between biology and geology is far fuzzier and more electrically charged than we ever imagined. These subterranean alchemists are not just surviving, they are actively engineering the Earth's crust, one electron at a time. For more incredible facts like this, don't forget to subscribe and turn on notifications.